Welcome to this last module of the course called Elements of Modern Physics. And in this last module, we will talk about relativistic quantum mechanics, and in particular, we will talk about Klein-Gordon and Dirac equation, though in without any interactions such as Coulomb interaction, etc. We will just talk about free particle Klein-Gordon and Dirac equations, and then we will talk about physics of elementary particles. So, that is the idea, and these later part, which is physics of elementary particles, will also be done in very brief. So, this is the structure of mechanics, classical and quantum mechanics, as it has been presented to you so far. So, we start with this fourth quadrant, and now if so this non-relativistic classical mechanics, in which we have studied Newton's laws, Lagrange's equation, etc., which tells us that under a certain force field, how the particle evolves, or the trajectory of the particle evolves as a function of time. And Lagrange's equation all further gives that which exactly is the path taken by the particle, because the Lagrangian density is extremum along that path only. And then when we went to relativistic classical mechanics, that is, we actually came to this 3 in the limit that your v is comparable to c. So, if the velocity of the particle is comparable to that of the speed of light, then these non-relativistic formalism, they do not work. And in the relativistic formalism, the main difference that comes in the form of space and time being coupled. And we have looked at special theory of relativity and Lorentz transformation, and we have talked about various phenomena such as which are paradoxes that arise because of the simultaneity problem. We have also looked at this in this second this quadrant, in which we have talked about non-relativistic quantum mechanics. In fact, we have spent the maximum time for this course in this non-relativistic quantum mechanics, where we have studied Schrodinger equation for various kind of potentials, including a constant potential, and then a particle in a box, and then harmonic oscillator, hydrogen atom, and so on and so forth. And this is true, or rather in the limit that you have the sizes of the particle to be small, or we are talking about the microscopic world, then these classical, these Newtonian mechanics, or the non-relativistic classical mechanics, that does not work. And the energy levels in the quantum mechanical systems are quantized in unit of h cross, or all these angular momentum, etc. They carry a scale of h cross, and so on, h or h cross, I mean basically the Planck's constant. Now, again one can go from here to here when you consider v to be of the order of c, and the relativistic quantum mechanics, we have not looked at it, and this is precisely what we are going to do here. And this would correspond to Klein-Gordon equation, Dirac equation, quantum field theory, etc. We will simply stop at this Klein-Gordon and Dirac equation. So, it looks like if you look at the 4 quadrants, the most complete description is given by this first quadrant, which talks about relativistic quantum mechanics, because this will go to the non-relativistic quantum mechanics for v to be much smaller than c, or it can go to relativistic classical mechanics when h cross can be neglected, or the sizes of the particle, or you talk about the macroscopic world, and so on. And similarly, the non-relativistic quantum mechanics can go to non-relativistic classical mechanics when so this way it is possible when the h cross is low, and this is possible again when v is much smaller than c. V is the speed of the particle, and c is the speed of light. Okay. So, we are really going to talk about these relativistic quantum mechanics, namely the Klein-Gordon and the Dirac equation. So, we start with Klein-Gordon equation. And in short, we will write Kg equation. Okay. So, we will write it as a Kg equation. So, whenever you build up a formalism for studying systems, physical systems, these have to be inconsistent with the special theory of relativity or the Lorentz transformation. And this is precisely the reason that the non-relativistic Schrodinger equation fell short of that requirement, because of you have a IH cross del psi LT or d psi dt equal to minus H cross square over 2m d square psi. We are writing just like a free particle wave equation or Schrodinger equation, but you can put a plus a v psi without a problem. Now, this tells you that this is a second derivative in space. Okay, so, this is second derivative in space, and this is a single derivative or a first derivative in time. Okay. But if you look at the Lorentz transformation equations, which are like x prime equal to x minus v t divided by 1 minus that v square by c square and so on and so forth, you see the x and t are at the same footing. So, if you write down or you try to apply these Lorentz transformation, this equation will not satisfy Lorentz transformation, and hence it will not be consistent with the theories of special relativity, and they have to be discarded when you are talking about V to be comparable to that of C. Okay. So, this is one of the main drawbacks of Schrodinger equation, which is only valid for V to be much smaller than C. In fact, there is no sort of spatial status of C here. C is just any velocity, but we know that from special theory of relativity that C is the ultimate velocity that a particle can attain. Okay. So, this is the reason that one needs to actually go and find out new equations whose solution would give a description of the particle when it is moving in this with this speed, which is that comparable to that of light. Okay. So, we have two things possible solutions. One is that upgrade the time derivative, that is d dt to d2 dt2, that is upgrade the first derivative of time to second derivative of time, so that it matches with the second derivative of space and hence will be Lorentz invariant. Or the second option is that you downgrade the your d square to just simply a d or a delta. Okay. So, not the Laplacian, but the first derivative with respect to space. This, when you do this, it is called as a Klein-Gordon equation, and when you do this, it is called as a Dirac equation, and we will see them separately for each of the cases. Okay. Now, just a priori, this KG equation or the Klein-Gordon equation has a difficulty in its interpretation, because it gives a probability density for particles to be negative. But however, if you interpret it properly, then it actually corresponds to probability charge density, which can be negative because of the charge be negative. So, initially there was a problem with this Klein-Gordon equation, and it is thought to be a perfect description for classical fields such as an electromagnetic field. But then with sort of proper interpretation of the charge density or the probability density, one can actually relate it to the proper wave equation or the appropriate wave equation for spin integral spin particle. Now, Dirac equation of course does not have any of the anomaly, and it is actually relevant to spin half particles such as electrons, and in fact, most of the time we actually talk about electrons. So, Dirac equation in that sense is very important. All right. So, we will start with the Klein-Gordon equation, as we have said. So, we do not have a dispersion which looks like E by E equal to P square by 2m, which is non-relativistic. Okay. This dispersion has been well studied. It is a free particle where E is proportional to P square, and the relativistic dispersion in fact is equal to p square c square plus m square c4. So, this is the relativistic dispersion. So, this is true at speeds which are of the order of speed of light. Okay. So, if you replace E by I h cross del del t and if you replace P by minus I h cross del, then this equation that is this equation, the relativistic equation. So, 1 becomes minus h cross square del 2 psi del t 2 equal to minus h cross square del square c square psi plus m square c 4 psi, and let us call this as equation 2. So, this is precisely the Klein-Gordon equation. If you write it a little more neatly, one can write this as a del square minus 1 by c square d2 dt 2 and a psi this is equal to m square c 4 divided by h cross square psi. And this operator is often called as the D'Alembert operator. It is written with a square sign, but we can simply keep writing the double derivative with respect to space, which is del square, and double derivative with respect to time, which is 1 by c square del 2 del t 2. Now, this is clearly Lorentz invariant because the space and the time derivatives are at the same footing, they have the same order. So, this is basically nothing but the Kg equation. And so, what is the difficulty with this equation? The difficulty comes when we try to write down the continuity equation, which is nothing but del divergence of j plus del rho del t is equal to 0. To remind you, j is the probability current density and rho is called as the probability density. So, rho in non-relativistic physics is simply equal to mod psi square, where psi is the wave function. So, if in order to find this, let us call this as equation 4. Let me see whether all equations are numbered. Yes, they are numbered and so on. So, to find rho and j, what we do is that we take this equation, equation number 3, and multiply this by psi star, and then take a conjugate of this equation and multiply it by psi and subtract the 2. So, this technique has been applied in the non-relativistic case as well to prove the continuity equation. So, the continuity equation is valid here as well. I will just write it that you multiply psi star to equation 3 minus psi conjugate of star the equation 3 star of that equation or conjugate of that equation, and take the the difference between the two. So, that gives that a psi star del square minus 1 over c square del 2 del t 2 this and psi, this is equal to psi star mc square. We can write the psi star later. So, we have these mc square by h cross square psi star psi m square c square. Okay. So, by h cross square psi star psi, and this can be called as equation 5. So, this is the first term that this term is here, and this term is, we can write it as psi and del square minus 1 by c square del 2 del t 2 psi star is equal to m square c square h cross square psi star psi. Okay. And let us call this as equation 6. I hope this is clear that we have taken equation 3 and have multiplied it by psi star, then we have taken the conjugate of 3 and then multiply it by psi and take a difference between the two. And so, if you take that then you can write down this equation 4, and this equation 4 then we have these definitions of the rho and j as, so putting in 3 in 4, putting in 4 or putting means after subtraction. So, let me write that after subtraction putting in 4 yields the continuity equations with the rho given by I h cross by 2 m c square psi star del psi del t minus psi del psi star del t. So, this is can be written as h cross by m c square and imaginary part of psi del psi star t del t. So, that is the imaginary part of that, and this is nothing but the rho, which is a function of r and t, and let us call this as equation 7. And this is the probability density, and the probability current density j, again a function of r and t, can be written as minus I h cross by 2 m and psi star del psi minus psi del psi star. That is the same definition that we have seen for the non-relativistic case, and let us call this as equation 8. Okay. If you assume a free particle solution now, for equation 3. So, equation 3, so we can write this down as psi of r t, this is equal to exponential I k dot r minus omega t. Okay. You may write an amplitude, you may not write an amplitude, it really does not matter. So, let us call this as equation 9, and if you substitute 9 into 3, that is the unsatz solution, 9 into 3, and what you get is basically k square minus omega square by c square equal to minus m square c square divided by h cross square. And if you identify so let us call this as 10. So, if you identify p is equal to h cross k and e equal to h cross omega, then your E square becomes equal to P square C square plus M square C4, and which gives 2 values of E plus and minus. This is equal to plus minus C, and we have P square plus M square C square. So, that is the energy, and now there are of course in addition to the plus energies, there are negative energies that are allowed as well. Okay. So, if you take this psi from 9 and then plug it in this expression which is 7. So, plugging 9 into 7, just to remind you that 7 is nothing but the this probability density, which is rho r t. So, if you do that, then what you get is that your rho r t that becomes equal to I h cross by 2 m c square. I write it again here just for convenience, psi star minus psi star del psi del t minus psi del psi star del t, and this with this definition, or rather these ansatz written in 9, it gives you E divided by m c square and a mod psi square. Okay. And where of course E is equal to this thing. So, E can take positive and negative values, and hence these probability density can be either positive or negative. But negative probability density defeats the traditional wisdom. It does not make sense to say that at a given region of space the probability of finding the particle is negative. Okay. So, since it does not make sense, it can be interpreted as a probability charge density, and then this plus minus sign associated with E, which is written in equation 11, that would be interpreted as since the charge can be both positive and negative. So, if it is a probability charge density, then of course, there is no problem. In fact, this has been told by a lot of people, including Pauli and Weisskopf, etc. In fact, they said that initially they said that this may not be a quantum mechanical equation, but these equation, the Klein-Gordon equation that we have talked about, is a valid description of classical field equations such as electromagnetic fields. Okay. So, now going back to this, so it should be interpreted as probability current density. Which can be both positive and negative. Okay, so this is the thing, or rather this is the issue with Klein-Gordon equation, which can be sorted out. Okay. So, this rho r t can be written as just putting the values of that. We have so this is equation set 12, and this can be written as this rho r t is equal to plus minus c and p square plus m square c square divided by m c square and mod psi square. Okay. So, this is equation 13, and these positive and negative values can be interpreted in the way that we have talked about. So, let us go back to equation 12, which says that rho r t is equal to E divided by m c square into mod psi square. So, if you take the non-relativistic limit, then the non-relativistic limit means that V is much smaller than C. So, the only energy scale that remains is E equal to m c square, because there is no kinetic energy, it is only the rest mass energy. So, this is called as the non-relativistic limit. Okay. So, this is if you put that, then rho r t becomes equal to, so m c square and m c square will cancel and will give you the non-relativistic form which you have used, or which you know to be true. So, that is equal to mod psi square. Okay. So, so basically the Klein-Gordon equation is important. There is an initial problem with interpretation of the probability density, but if you do that as the probability charge density, then it can take positive and negative values, and it gives you the correct non-relativistic form, which is known to be mod psi square. Okay. But of course, it applies to the integer spin, I mean basically applies to integer spin and spin 0, basically spin 0 particles. Okay. Or let me write that does not apply to spin half particle, which is what we want to find. And this is what the Dirac equation is going to give us. So, we will study Dirac equation. Okay. So, we write down Dirac equation, and what we have said is that in order to write down a relativistically invariant wave equation, and initially there was no hint that it is for spin half particles, but later on it emerged. And not only for spin half particles, there are positive and negative energies as well. So, this is quite important, and the way it started is that Dirac linearized the equation, the Schrodinger equation. In fact, as I said earlier, that he downgraded the the space derivative from a double derivative to a single derivative. Okay. So, the linearized Hamiltonian it looks like H is equal to C alpha dot P plus beta m c square. This is the the kinetic energy, and this is the rest mass energy, alpha and beta, these are matrices, and beta, they are matrices. Okay. And we do not know the rank of the matrix, and neither we know the form of the matrix, but they are matrices for reasons that we are going to tell you right away. But one is that alpha has 3 components, alpha x, alpha y and alpha z, sometimes called as alpha 1, alpha 2 and alpha 3, and beta is another, and so on. And there are certain properties that are going to emerge of these alphas and betas, which necessitate us to take these forms, that they are not scalar quantities, they are actually matrix quantities. And if you write this as equation 1 and then you plug it into H psi is equal to I h cross d psi dt. So, it is a linearized equation. So, one obtains E minus C alpha dot P minus beta m C square. This psi will be equal to 0, and we can use E equal to minus A I h cross, sorry, E is equal to I h cross del del t, and P is equal to minus I h cross del. Then this thing looks like this equation, it is I h cross d dt or del del t, let me write it as del del t, minus I h cross c alpha dot del minus beta m c square psi equal to 0. Okay. So, this is called as a Dirac equation. And let us call this as equation 2, and this equation is the most important equation. Now, this equation is Lorentz invariant because you have a single space derivative, which is del, and you have a first order. What I mean to say by single is that first order space derivative and a first order time derivative as well. Okay. So, what we do is that in order to proceed, we will operate this equation by these operator, because this operator acting on psi gives you 0. So, we do that because you have a quadratic, E square is equal to P square C square. So, we want to see that how this equation can be related to this relativistic dispersion, which is E square equal to P square C square plus M square C4. So, what we do is that we operate this equation by these whatever is underbraced here, and that gives us E plus C alpha dot P. I am writing this equation which is one step above. So, there is the P is negative. So, there is a plus sign here. So, E plus C alpha dot P plus a beta m C square operating on E minus this C. So, if you write it in terms of P, then there is a minus sign, and if you write it in terms of P equal to minus I h cross del, then there is a plus sign. So, we should not make the sign mistake. So, E minus C alpha dot P minus beta m C square, and then acting on psi will give you 0, and this can be simplified. It will give you a big expression, but there is nothing much to worry about. So, you simply operate it, or rather multiply it, and we have these E square minus C square, then you have a alpha x square P x square plus alpha y square P y square plus alpha z square P z square. So, this is one term. Then there are cross terms which come as commutator or anti-commutator, alpha x plus alpha y plus alpha y alpha x, and a p x p y. Then we have alpha y alpha z plus a alpha z alpha y, and a p y p z, and then we have these plus alpha z alpha x plus alpha x alpha z, and then we have this p x p z, p x p z. Okay. So, this is one term, and I mean these are, so this alpha squared term and this all these cross terms, etc. And then there is a minus m square c 4 beta square, and then minus m c square, and then we have a alpha x beta plus beta alpha x. This is just simple multiplication. So, you have to do it carefully. There are 3 terms and this is a 3 by 3. So, there will be 9 terms and so on. So, plus alpha y beta plus a beta alpha y, this is p y, and then there is the last term is alpha z beta and beta alpha z, p z and psi, this is equal to 0. Okay. Now, what you do is that you compare it with E square equal to p square c square plus m square c 4. You see that there is a p square term, and which means that these are like terms. So, there is like if I open it, it will be p x square plus p y square plus p z square and all that. So, all these cross terms, these terms will all be 0, because there is no term that connects different components of p in this equation. So, that tells us that alpha and beta, so they satisfy these equations, which these equations are, let us call them as, so let us call this equation as 3. And these equations are like alpha x square equal to alpha y square equal to alpha z square equal to beta square is equal to 1. So, that gives that all these operators, or rather these quantities, the alpha x, alpha y, alpha z, they square up to unity, each one of them individually, and the further these, so let us call this as 4a, and then alpha x alpha y plus alpha y alpha x equal to alpha y alpha z plus alpha z alpha y equal to alpha x alpha z plus alpha z alpha x. This is all equal to 0, because there is no cross term. So, this let us say 4b, and not only these alphas, they anti-commute with themselves, alphas also anti-commute with beta. So, alpha x beta plus beta alpha x, that is equal to 0 as well, because if you see these things, there is no linear term in p in the dispersion in the E square form. So, they would be 0 as well. So, this is equal to alpha y beta plus a beta alpha y equal to a alpha z beta plus a beta alpha z, and all this they will be equal to 0. So, that tells that these squares are unity, and all of them anti-commute with each other. Now, that tells us that they can't be simple numbers because of this anti-commutation relations, and their all of them squaring up to 1, that is only possible for matrices. So, alpha and beta are matrices, but we do not know what is the rank of the matrix and so on. But at least we know that they are not a single component object, they are they are basically a column vector which has, or rather a matrix, not a column vector, sorry, it is a matrix, psi is a column vector. And because of the hermeticity of H, H is of course Hermitian, and because of that alpha and beta are Hermitian as well. Okay. So, we got a few very important inputs, or rather very useful inputs. One is that while linearizing this Schrodinger equation or making it relativistically invariant, we wrote down this equation, which is the Dirac equation, which is H minus or H equal to C alpha dot P plus beta MC square. Operating it on the wave function and writing down the equation, the corresponding wave equation gives us E minus C alpha dot P minus beta MC square equal to, operating on psi equal to 0. And in order to get further insights into the problem, what we did is that we have multiplied these operators. So, from the left and on this Dirac equation, the same operator that appears in the Dirac equation, we have multiplied it there. Once that is done, we get a long equation including this px square, py square, pz square term, and then the cross term px, py, and then the term that are linear in x, and there is also one term that is completely independent of x and depends on the rest mass energy. If you compare these with this equation, the equation that is the relativistic equation, then we understand that there are certain relations of alpha and beta that emerge, which are written in 4a, 4b and 4c. And because of these relations, we are forced to think them not as single numbers, but they are matrices. We are yet to ascertain the rank of the matrices or the shape of these matrices. Now, these are, if we accept that they are matrices, then we can take arbitrarily, we can take one to be diagonal and others to be off diagonal. And let us take beta, this purely kind of convenience, beta to be diagonal and all other alpha I, these are off diagonal. Once again, it is not clear at this moment that what is the size of the matrix or what is the rank of the matrix, so to say. Okay. So, why is this taken? Because one is diagonal and the others are off diagonal, and that is the only way that they can commute or rather they can anti-commute, because if more than one is diagonal, then they would not they would not all amongst themselves, they would not anti-commute. So, this is an essential requirement. Now, if you ask me that why beta has been taken as diagonal and the other three are off diagonal, you can there is no embargo on that. You can take one of the four to be diagonal and the other three to be off diagonal, but this is the standard procedure that is kind of followed. Okay. So, the squares of the matrix that become unity. Beta square equal to 1 and beta is diagonal, that tells us that beta has eigenvalues which are equal to plus and minus 1. Okay. So, if these are the eigenvalues, then beta and beta being diagonal, so beta will have in its diagonal elements we will have this, and just to make things a little general, we can write this not as 1, but like this, which would stand for a sort of big matrix which is like this, and it is like a 1 0 0 and so on, and then 0 1 0 so on, and then 0 0 1 so on, and then so on here, and similarly all these are 0, and then we have these as So, basically we can choose this as not as 1, but as minus 1, and then we have a minus 1 0 0 and so on. It is still diagonal, of course, but with 1 1 it becomes an identity matrix which will commute with everybody. So, that is not a possibility. I wrongly wrote it as plus 1, but it has to be minus 1. So, this is 0 minus 1 0 and so on and so forth. Okay. So, that is the size of the matrix, but we really do not know, or shape of the matrix rather, and we have said that alpha and beta are they are Hermitian matrices. Now, if beta has a structure like this, and each of them, it's some kind of an m cross n matrix. So, each of these is like a m cross n matrix. Okay. So, each of these diagonal blocks is like m cross n matrix. So, this is like an m cross n matrix, and this is like an m cross n matrix as well, and we are yet to ascertain that what are the values of m and n. Now, very important input comes when we look at the anti-commutation relation between the alpha x beta plus, or any of these, not only alpha x, but alpha y, but just we are looking at this this alpha x. So, beta alpha x, this is equal to 0. Okay. So, if you take the jkth element, then what happens is that the alpha x jk and these beta j plus beta k, this is equal to 0. Now, this beta j, beta k are the diagonal elements, and because it has eigenvalues plus 1 and minus 1, so beta j can be equal to beta k can be equal to, say, either plus 1 or minus 1. In both the cases, your alpha x is equal to 0. Okay. If beta j is not equal to beta k, which means one of them is plus 1 and the other is minus 1, in that case alpha x j k may not be equal to 0. I am not saying not equal to 0. So, may not be equal to 0. Okay. That is because of this, in order to satisfy this equation. So, once again I will just go over it. If beta j and beta k both are same, then they would add up either both plus 1 or both minus 1. In that case, necessarily alpha x j k will have to be equal to 0, and if it is not equal to, they are not equal, that is, one is plus 1 and one is minus 1, then that could be 0, then alpha x may not be equal to 0. And in fact, it is clear that it is coming from that structure, that these alpha x and similarly alpha y, because alpha y obeys the similar relation as we have written here, this equation. So, and alpha z as well, that satisfies the same relation as well. So, all of alpha x, alpha y and alpha z are off diagonal, and this is what we have kind of started off with. And when we mean off diagonal, which means that it has a structure that is, these are zeros and there will be some non-zero elements here, these will be some non-zero elements. Okay. And in fact, this alpha matrix can be written as, we will just show that, as a 0 and sigma and sigma and 0, and where sigma are the Pauli matrices. So, sigma x, sigma y and sigma z, and then automatically it tells you that it becomes equal to a 4 by 4 matrix. So, beta is then equal to, it's like 1 0 0 0 0 1 0 0 0 0 minus 1 0 0 0 0 minus 1, and these alphas will be formed by this these 2 by 2 matrices, which are sigma x, sigma y and sigma z. Just to remind you that sigma x is equal to 0 1 1 0, sigma y is equal to 0 minus 1 minus I 0, and sigma z is the diagonal one, which has 1 0 0 minus 1. Okay. So, now why is it 4 by 4 and not larger than that? There are two sort of rational or two reasons behind that. We can say that any matrix, suppose first we say why it is not a 2 by 2 matrix and it is a 4 by 4 matrix. So, if you for any matrix, any 2 by 2 matrix, which can be written as linear combinations of the Pauli matrices and the identity matrix. Okay. And if it can be written as in terms of the Pauli matrices, then they will commute, and clearly these matrices, they anti-commute with each other. So, they can't be 2 by 2. And so, basically also it is not difficult to show that if they are 2 by 2 matrices, then a fourth matrix really you can't find a fourth matrix that anti-commutes with the all three. And this again reiterating the solution, or rather this statement, that for any 2 by 2 matrix, like a matrix which is A, B, C, D, that can be written in terms of something sigma x plus something sigma y plus something sigma z, that is some coefficient sigma z which are formed of A, B, C, Ds and so on, and sigma z, and plus something which is sigma 0. All right. So, if that is true, then of course, these matrices won't anti-commute with each other, because each one is like a sigma x and or sigma y or sigma z. Okay. So, let me give you another proof which is probably even more mathematically sound. And so, we start with this anti-commutation relation, which is alpha I beta equal to minus beta alpha I, okay, where I is x, y and z. So, if I take a determinant of both sides, alpha I beta, which is equal to determinant of minus 1 and determinant of beta alpha I. So, this becomes equal to determinant of alpha I into determinant of beta and equal to determinant of minus 1 and the determinant of beta and determinant of alpha I. Now, you see that determinant becomes kind of a number. So, determinant of alpha I, determinant of beta will cancel from both sides, and that gives us the determinant of minus 1 is equal to 1. Okay. Now, for general n cross n matrices, this determinant of minus 1 it's equal to minus 1 whole to the power n, and a minus 1 whole to the power n can only occur, which becomes equal to 1, can only occur from n equal to 2, n equal to 4, n equal to 6 and so on. So, the simplest one or the smallest one is n equal to 2. That tells us that these alpha matrices are really like these matrices that we have written earlier. So, these are 2 by 2 matrices, these are 2 by 2 matrices and 2 by 2, and similarly for beta as well. They should definitely have the same rank in order to follow all these anti-commutation relations. So, now it is clear that all 4 of them are really 4 by 4 matrices, and it is important to note that these 2 of them actually correspond to positive and negative solutions, energy solutions, and the other is basically because of the spin, which is like the Hilbert space is 2s plus 1. It is also important to note that we did not have an analog of spin in non-relativistic quantum mechanics. It only came naturally with in an effort to linearize Schrodinger equation and make it Lorentz invariant. It came as a dividend. So, let me finally write these equations, which are 1 0 0 0 0 1 0 0 0 0 minus 1 0 0 0 0 minus 1, that is beta. Alpha x is that sigma x there. So, it is 0 sigma x 0. So, that is 0 0 0 1 0 0 1 0 0 1 0 0 and 1 0 0 0. Okay. You can check all of them to be they are Hermitian. So, even though alpha y will have I there, but it is still Hermitian. So, 0 0 0 minus I. So, now it has a structure which is like a 0 sigma y sigma y 0. Okay. So, this structure is reflected here, and this structure is 0 sigma x 0, that is reflected here. So, 0 0 I 0, then it is 0 minus I 0 0, then I 0 0 0. Okay. And finally, alpha z, which is equal to this sigma z. So, sigma 0 sigma z 0. So, that has a distinct form than beta, although it looks like, so it is a 0 0 1 0 and 0 0 0 minus 1, then it is a 1 0 0 0, then it is a 0 minus 1 0 0, and so these are the 4 matrices. Okay. Now, assume a solution, free particle solution. Psi I r t, so this is equal to u I exponential I k dot r minus omega t. So, if you substitute this in the Dirac equation, we have kept of course amplitude, and you get a 4 by 4 equation. So, now the Dirac equation, unlike Schrodinger equation, which was just a single equation, now it is a matrix equation. So, there will be 4 coupled equation. So, it is E minus m c square u 1 and minus c p z u 3 minus c p x minus I p y u 4 equal to 0, there is no u 2 here. The second one has E m c square. This obtained by putting all this alpha beta which are given there, and then putting this unsatz solution. U 2, this is C p x plus I p y sigma u 3 and plus C p z u 4, that is equal to 0. Again, there is no u 1 here. Then we have a E plus beta m c square, beta has been put, m c square u 3 minus c p z u 1 minus c p x minus I p y u 2, this is equal to 0, and E plus m c square u 4 minus c p x plus I p y u 1 and plus c p z u 2, that is equal to 0. Okay. So, these are 4 by 4 equations. Now, they have a unique solution only when the determinant of the coefficient matrix is 0. And this gives us these unique solutions, and these solutions for, so there are these two energies E plus and E minus. So, corresponding to E plus, we have E equal to E plus, that is the plus sign in front of this. So, if you write this E to be equal to plus minus C p square c square plus m, sorry, not c square, c already has been taken out. So, it is p square plus m square c square. So, this plus sign E equal to E plus. So, you have these u 1, u 2, u 3, u 4, and these are so there are these two linearly independent solutions, and these linearly independent solutions are C p z divided by E plus m c square and C p x plus I p y divided by E plus m c square. Let me write this neatly. So, this is one, and the other is the two linearly independent solutions are it is a 4 by 4. The two eigenvalues are E plus and the two eigenvalues are E minus. So, it is a C Px minus Ipy divided by E plus mc square and minus Cpz divided by E plus mc square. Yeah. So, these are the two linearly independent solutions for E plus, and for E minus we have these U1, U2, U3 and U4 as these Cpz divided by E minus mc square, Cpx minus Ipy divided by E minus mc square, and 1 and 0, and the other solution is C Px minus Ipy divided by E minus mc square, and Cpz divided by E minus mc square, and 0 and 1. So, this is corresponding to E minus and that corresponds to E plus. So, these are the two linearly independent solutions. So, we got positive and negative energy solutions, and then we have as an important dividend we got a sort of a matrix structure of this Hamiltonian which corresponds to up and down spins which are relevant for the spin half particles like electron. So, electron, so it is basically the spin has this twofold structure as well as the energy, the two energies plus and minus, that makes it 4. So, it is basically a 4 by 4 equation, or rather the 4 by 4 Hamiltonian, whose solution gives us all these things for the free particle. Of course, we stop at free particle, but the problem can also be solved. Suppose you want to solve hydrogen atom, so that solution would have to be done in presence of a the 1 over r kind of a Coulomb potential. We will not do that. From here on, we will discuss very briefly the physics of elementary particles. Okay. So, we will stop here. Thank you.